So this morning we're going to tackle this topic of complex numbers. And you recall when we were doing that topic on quadratics, you ended up with some situations where when you try to use the formula to solve the quadratic equation, a strange thing happened. Sometimes you have an equation where when you substitute into the formula, the b squared minus 4ac under the square root sign, you end up with something like this, where you have a negative, let's say -4. And that situation kind of stumped you, And then, well, what do we do here? Well, it is situations like these that made the invention of a new set of numbers necessary, right? And of course, mathematical thinkers thought of these situations and others, and they came up with the idea of let's create a way of evaluating the square root of a negative number. And there is where complex numbers were born out of. As a matter of fact, something called the imaginary unit was invented. So what's the imaginary unit really, right? We'll designate it with the letter I. And what the imaginary unit really is the square root of -1. That's a simple definition of what I is. It's the square root of -1. Before then, they didn't have a way of evaluating -1. And this well illustrates how new mathematics is created. We come up with a situation where something like this was never defined before. There was no way of finding the square root of -1. And therefore, mathematicians thought of, let's find a way of defining how we find the square root of a negative number. And the idea of creating what we call an imaginary unit came up, right? And they defined it as square root of -1. And from this was born this whole branch of mathematics called complex analysis, right? And if you study mathematics to that extent, you're going to see, or you're going to be exposed to that entire branch of mathematics where complex analysis is involved, and its applications as well, right? Has lots of applications, especially in physics and so, right? Electricity in particular, you'd find the application. So this is a general, definition. If you have the square root of -r, and r can be any real number, right? Positive real number. The square root of -r is I root r. The reason why you notice they have here the square root r is behind the I rather than in front, because sometimes people tend to write this, and I just want to show you what people tend to write. They put the square root and they put the r here, and sometimes instead of writing the r out here, they tend to put it here. They tend to put it under the square root sign, right? And that's not what this means, right? So because of this, to avoid this, well, they decided to write it like this: I root r, right? You can still see textbooks and internet articles, and so write it like this: root RI, but the I is well outside of the square root sign. You can still see that, right? So this is not a law or a rigid rule, right? You might still see it written differently. And these are some examples. Right? Because the square root of 4 is nice and round, you don't have to use that square root sign over the 3. And in the lesson after this, we're going to talk about what we call swords, and you'll be helped to understand this root 3 business, what it's all about, and so on, right? And the simple reason is because we can't write it exactly. Square root of 3 is not an exact decimal, that we can write, and therefore, instead of writing a non-terminating decimal or so, we just put root 3, right? Looks more concise. And you'll notice a pattern here with powers of I. So I square is -1. Because if the square root of -1 is I, then I square is -1, right? That comes from the very definition. But what about higher powers of I? Well, if you were to play around with I cube, you will see that it's I by I by I. So I by I will give you -1 times I will give you -I, and so on, right? I to the 4, it's like I square by I square, so it's -1 by -1, and so on, right? And there's a pattern. If you were to analyze it, there's a general pattern. And when the numbers get very large, when the powers get very large, this is a simple rule that you can use to evaluate. Right? So you have a very large power here, I to the 23rd power, right? So what do? Well, you know that I to the 4, you see there's 1, right? Therefore, you divide the power that you have there, 23 by 4, and you have a remainder of 3. So if you were to break up I to the 23 and, I times I to the 4 by I to the 4, you'll end up with a string of them times, and the last term will be I to the 3rd power. All the I to the 4s will become 1s, and I to the 3 is -I. Therefore, I to the 23rd is -I. Right? So just in case you don't quite understand the example, let me highlight it here. So I to the 23rd is like I to the 4 times I to the another 4 times another I to the 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 3 this time, right? So 4, 4, 8, 12, 16, 20, yes. So that would have given us our I to the 23. So each I to the 4 is really 1, because you're seeing it over here. Look here, right? So all the I to the 4s will become 1. And then I to the 3rd power, you see here, it's not hard to figure out, is that. So I to the 3rd power is -I, so I to the 23 is -I, right? That's an easier way to evaluate those very, very large powers, right? That's something just by the way. That's an interesting fact. Let's have a little bit more, examples involving the imaginary unit now. Some further examples. So I root 3, you're squaring it, what happens? You know that I square is -1. Root 3, the square of that is 3. Right? So your answer is -3. Here is a situation that we were talking about earlier, where you have a quadratic and you might very well end up with a situation where you have to find the square root of a negative number, right? So you have to find the square root of -12. Well, we have a way now of evaluating that, right? So evaluate -12, it's plus or minus I root 12, right? So we have a way now of evaluating -12. And now we can proceed with our solution, right? Okay. So these are our two solutions, right? You will want to note that, and as you continue now and go into the topic of complex numbers, you will notice that when we solve a quadratic equation that has complex roots, the two roots are always what we call in conjugate pairs, meaning that, well, okay, like you see here, one is positive 2i root 3, the next one is negative 2i root 3. In other cases, let's say you have a solution that is 1 plus I, you know that the other solution is 1 minus I. Don't waste time and do any calculation. The other one will be 1 minus I, right? So now that we're introduced to the complex, the imaginary unit, we have to come up now with a bigger universal set than the real numbers, because I think up to this part of your education or your exposure to mathematics, you think that, well, the real numbers is the universal set for all the other numbers that you know, right? So thus far, your universal set was the set of real numbers. However, now that we come to find out about about imaginary numbers, we have to widen. We have to widen our horizon now and come up with a new universal set. And that universal set is the set of complex numbers, right? And if I were to, so let's say we have a Venn diagram here. So your universal set now is a set of complex numbers, which is like a capital C. The textbooks will see this area here is a little thicker, it's kind of like a shadow, right? But it's a C. You'll see it in your notes and so on. So real numbers are here, right? And outside of real numbers are imaginary numbers, right? So real, long ago, well, we had all of these other numbers inside here, right? Whole numbers and natural numbers and all the other numbers in there. Now we learn of imaginary numbers now, right? Imaginary numbers. And you widen your horizon now to see that we have a new universal set. is a set of complex numbers, right? So complex numbers include all the real numbers, all imaginary numbers, right? And inside here, you would have numbers that is a combination of the two, right? It has a real part and an imaginary part, right? So all real numbers are complex numbers. All imaginary numbers are complex numbers. And there are complex numbers that are outside here that has both a real and imaginary part. And let's deal with that in the next slide. Good. So just to avoid any confusion, I just mentioned when I looked at the Venn diagram that all real numbers are complex numbers. And indeed, you can take a real number, let's say number 2. 2 can also be written as 2 plus 0i. So it has this form, a plus bi, right? So it does fit the requirement here that it's a complex number because it has a real part, it has an imaginary part. It's just that imaginary part, the coefficient, right? Or what it is here, is 0, right? Let's take an imaginary number. Let's say 2i. Now you want to think of this as 0 plus 2i. So it does have this form. It's just that the real part is 0. And then there are all those numbers that have, of this form, like, okay, 2 plus I, 3 minus I. So those numbers now, they have both a real part and an imaginary part, right? So complex numbers are all real numbers, all the imaginary numbers, and those numbers that has a real and imaginary part, right? I mean with non-zero coefficients. Huh? So all of this, is widening your horizons a little to think a little further than you were exposed to before, right? So it's not hard mathematics, it's just new. And a bit of reading, some more reading in the area, doing some arithmetic with complex numbers, and so will make you more familiar with them, and you'll be able to get familiar with them and be proficient at using them and so on. So we're going to do a little bit of arithmetic with them, but let's first try to put them maybe on a graph. And in graphing them, we use what we call a complex plane, right? I think you're familiar with the Cartesian coordinate plane, right? The XY. So now we're talking about a complex plane. A complex plane. And instead of the X and Y axis, you have what we call the real axis and the imaginary axis. So where the X-axis used to be, that's what we call the real axis. And the Y-axis is the imaginary axis. Let's try graphing a few of complex numbers. So let's graph a few, right? Graph these 4. Minus 2 plus 5i That's 2 plus 2i, then 4 minus 3i, and then minus 4 minus 3i, right? In some textbooks, you'll see the writer actually connect the origin to the dot, right? And they'll even put an arrow. So one of the things you will find out in later on in your reading of complex numbers is that the complex numbers cannot be ordered. What do I mean by that? When we deal with real numbers, we tend to, say that, well, this real number is greater than that real number, right? However, we don't order the complex number saying that, okay, 4 minus 3i is somehow greater than minus 4 minus 3i, right? We don't order it. But in real numbers, we do that, right? You later on, you can figure out all of that in your reading, right? What we can talk about indeed is you can talk about the modulus or the magnitude of one complex number being greater than the other, right? But you just can't say which one is greater than which one in terms of size, right? No, not size, sorry, based on their position. So let's do a little bit of arithmetic, with complex numbers. You want to add them, subtract them, multiply them, and I'll use the term divide them until when we come to that, we have another name for it. So let's see. So this is addition. How do you add them? Well, you simply add the real parts and the imaginary parts, right? Just like how in the rest of algebra, you add the x's and you add the y's. You can't add the x and y, right? Well, same thing here. You add the real numbers and you add the imaginary numbers, right? Not hard, shouldn't be hard. So the minus 1 and 3, you add them, then your 2i and 3i, you add them together. Subtraction, well, same thing. You subtract the real ones and you subtract the imaginary ones. So what you could do is just remove the bracket too, right? Remove the brackets using distributive law and then simplify. They did it a little differently here, right? You have to be very careful with your signs. 2 minus this 3 is okay here, but over here, notice minus 3 minus 7, right? Careful with that. I like to do it safely by removing the bracket, right? I like to do this. This is what I like to do. 2 minus 3i minus 3 plus 7i, right? And this 2 minus the 3 will give you minus 1. And minus 3 plus 7i will give you 4i, right? I think that's what the yeah. So be careful with those brackets. Then a more complex one, no need to worry, right? You treat them just like you treat x and y's and whole numbers and so, right? Yeah. Add all the real numbers, add all the, well, whatever sign is in front of you, right? Add or subtract as need be. So a little bit of multiplication. Right? So you multiply just like though the minus I is like a minus x in front of you, right? You multiply. Then of course, when you multiply, you see you have a I square, and you know I square is 1, minus 1, sorry, right? And you simplify after that. Simple. Are you following? Getting no feedback from nobody.
Yes, sir, following.
Yes, sir.
Look at this one. It's like 2 binomial now. You're multiplying, right? Treating I is just like x's, you know, you multiply. But when you finish, you notice this I square at the end there. You have to simplify that a little further, right? So you know that I square is minus 1. So you continue your simplification. And you get that. Am I going too fast? Especially when it's new mathematics, you know. And sometimes people feel, hey, you got to slow down with it. I want to show you it's not hard mathematics. It's just new, you want to get used to it. And I wanted to approach it like you have a new cell phone. You don't say, man, the cell phone hard for you, being able to learn it. You know? You're excited, you spend a lot of time with it. And before long, you are, you know, you are a wizard using it. Same can be true of this matter of complex numbers. Just a little bit of practice. So we dealt with addition, subtraction, multiplication. Now we're going to look at but we're not going to call it division, right? Let me see if I can go back. Sorry.
Let me see one get on the thing one.
Yeah. I think what has happened here is something has come into the slide that is, I should say, came in orally, right? The problem was supposed to be this. We want to divide 3 plus 11i by minus 1 minus 2i, right? So to do that, well, instead of the word division, you will hear the term that we want to realize the denominator, right? And the word really means, when you watch the word realize, it's like R-E-A-L. You want to make it real, make the denominator real, right? That is why they say realize, right? If I just pronounce it, realize. You understand? I say you're fully Americanized. You go to America for a 1-month holiday. When you come back, what's up, guys? Does the cow still eat grass? You know, you're fully Americanized in just a month. Well, what we want to do here, we want to realize. Well, you don't say realize, you say realize the denominator, right? And it's the same as you dividing the numerator by the denominator. What you do for that is you multiply both the numerator and the denominator by what we refer to as the conjugate, right? Minus 1 minus 2i is the denominator. You multiply both the numerator and the denominator by the conjugate of that. And what I mean by that, you simply change this minus sign here in front of the imaginary part to positive, right? So you multiply by -1 plus 2i over -1 plus 2i, right? And when you do that, this is what happens. So you do that multiplication. It's a lot of work. It's quite a bit of work. I wonder what is it? My internet is slow, or there's too much time lapse in the animation. Yeah, so you simplify that. I don't know if you're following and you're doing multiplication as we go along, right? And when you simplify all of that, what you realize is that in your denominator, you no longer have a complex number. It looks like that, and you can simplify it looking like this, right? So notice you don't have a complex number anymore in the denominator. You have a very simple form, right? -5 minus I. Not all of them will turn out like that. Some of them will have some horrible fractions. Well, we'll come to some that are written with sort form in just a moment, right? When we finish this topic, we'll go on to sorts. So the process, we don't say we're dividing 3 plus 11i by -1 minus 2i. We say you're given this rational complex number, like a fraction, one over the other, and you're told to realize the denominator, right? So some in the textbook, they will say divide this one by that. They'll give you a rational complex number and say realize the denominator. And that's your answer, right? And we spoke about the complex numbers, that we don't order them, but we can find what you call the modulus or the magnitude. That means the line segment from the origin to the complex number. What's the length, right? And this formula can be used to calculate the modulus or the absolute value of the complex number. And these are some examples, right? And that's the symbol there for modulus, those 2 bars at the side. Yeah. Right, and if I were to, there's also, and if you do some reading in the notes, apart from the modulus or the size of the complex number, you can find out what's the argument, they call it, or the angle the complex number makes with the real axis here, right? And let's see, this is what, -2 plus 5i. So -2 is here. Let's say there, -2. And let's say down here is 5. And let's say this is the point here. So, oh my. Can I undo that? Undo, yeah. So this is the point here. I'll draw from here. Yeah. And this angle from here to here is called the argument. It's called the argument of the complex number, right? And let me see if I can, what's this? Tan inverse. Well, I'm not going to get into it because the trigonometry involved might be beyond you, right? But this angle here can be found And that angle becomes, well, I think if you find tan inverse of 5 over minus 2, will give you a negative value, right? You'll get a negative value. Could somebody find tan inverse? Tan inverse of negative 5 over 2. Can somebody find that for me? I think they'll give you a negative answer.
Negative 68.2.
What is it?
Negative 68.2.
I'm not hearing that clearly.
Negative 68.2.
Negative 68.2?
Yes, sir.
Good. So that's this angle here, right? That's this angle here. And I will leave it up to you to figure out that if this is negative 68.2, right? That's what the calculator gives you. What is this angle here? Right? And that here, there, well, you can see, right? That shouldn't be hard. If this is negative 68 here, right? Could somebody tell me what this whole angle will be here? Where will be 68? If this is 68.2, right? Wouldn't this here, this angle here, be 68.2 as well? 68.2?
Yes, sir.
And then what will this angle be? Let's call this alpha. Alpha equal, how will it be?
111.8.
And how you get that?
180 minus the 68.2.
180 minus 68.2, right? And you will get, what is it, 111? What do you get? 111.8.
8.
11.8.
11 or 111?
111.8.
Something around with y'all, like when I 0.8, right? Yeah.
111.8, sir.
Yeah. Right? So, I mean, it's a lot of trigonometry. That's why I'm not going through it too much in the lecture, right? But that now becomes what we call the argument of the complex number. So you get the magnitude and then the argument, right? So you can actually describe a complex number in terms of its magnitude or modulus or absolute value and its argument, right? I want to just highlight that a lot of this is in the notes, so please read them. And they're asking which one is closer to the origin. The magnitude should tell you, right? Because the magnitude basically tells you what's the length of the line segment from the origin to the complex number. And that brings us to the end of the lecture, right?